Where is that chat box? It is here. What is the answer? No answer? Hello, Mr. Singh. What is the answer? Square root of I, what is the answer?
1 by root 2 plus iota 1 by root 2. I think it was that.
Yeah, you are right. But it's simply one angle 45 degrees. This point with 45 degrees. See, 90 degrees is I, square root of I is half of its rotation, 45 degrees. Okay.
Yes, sir.
Right. Then what is I raised to I? What will be that? All of you can try. I raised to I. Try, then it will become interesting. That is the reason I have put this question. So better, I think you tell through audio rather than going to the chat box. Sing, can you tell I? What is I? I can be written in another way. That's a proof. Okay, if you are not come to that, we will come to this right hand figure. So this is a very important figure. Anybody who is, particularly in the electronics and communication, electrical and electronics, and even for mechanical engineers, civil engineers, this figure is an extremely important figure. And it is far-reaching effect for this particular. We are not going to cover in detail, but then that much time will not be there. This is again the same circle on the left side, is shown a little bigger. Now, I have shown this is a unit circle in the complex plane. I have taken a vector of unit length with an angle, arbitrary angle theta. Now, the projection of this on the real axis will be cos theta, and the imaginary axis will be sin theta. That means I can write this vector as cos theta plus I sin theta, showing that the I axis component is sin theta. That was the meaning. Here symbol is not there because real axis we don't give a symbol. But in normally, if you call x here and y here, and there is a unit vector I and a unit vector j here, then we would have told I into cos theta plus j into sin theta. That is the way we used to write ijk, way of writing vectors, unit vector in terms of unit vectors. So now this is an arbitrary vector as a point on the complex number plane. It is represented by a vector with a theta angle. So this is okay. Now, see, this particular way of representation is also known as, you see, E. This E today we cannot discuss, but I'll ask you later. There is a lot of significance for this fellow, small e. To the power I theta is equal to cos theta plus I sin theta, which is same as this particular one. That means this particular point is nothing but e raised to I theta. Here e raised to I theta 2, 3, and so on. So now assume that my point is moving along the circle in the counterclockwise direction with an angular velocity omega radians per second. That means at time t, I would have covered an angle omega into t, that is theta of t is omega into t. That means this vector is going to rotate again and again with an angular velocity of omega radians per second. And that exactly is what e raised to j omega t is written. What is the j here immediately, I to j? They are same here, Only thing is electronics engineers, because this small I is used for current, that electric current, and they usually use the symbol J. That's the only reason. Otherwise, it is the same imaginary thing I only. So this is, as you all know, cos omega t plus I sin omega t. So it's called a complex sinusoid. And in communication, in circuit theory, in Fourier analysis, in Laplace analysis, everywhere you use this, and consists of two sinusoids. Great stuff. I think you should know about small e also to understand its beauty. Okay. Having said that, this vector, suppose it rotates and coming and reaching this particular point, -1, 0. Let us interpret it now in a different way. This point can be called e raised to, I said this point is e raised to I theta. This is e raised to I pi by 2, and so on. So this is e raised to I pi, and that is equal to -1. And therefore, I can write e raised to I pi plus 1 is equal to 0. And this is called Euler's identity. And this equation, this identity is called the jewel of mathematical, what do you call it, philosophy, by many Nobel laureates, including Feynman. And the first one I don't remember. This is the second most important mathematical identity in the history, and is Euler's identity. You know why it should be more called like the second most important jewel of mathematical thing and all that? That is very important. We should ask like that. See, usually pi comes from the circle, sphere, and all. Pi 2 pi r, pi 4 pi r square, area of a circle. And I comes from the complex number, and E comes from another calculus. It's a very funny thing. Today we are not going to discuss about it. This is coming from another world. I comes from complex number theory. Pi comes from geometry. The zero is invented by Indians. This is also supposed to be a very great number. And 1 is also supposed to be a very great number. We say 1, 2, 3, 4, 5 things it brings together. It welds together 5 different aspects. And that is why this equation, this identity is one of the famous jewel of mathematics. Now, why I said this is an opportunity for all of you to listening the complex number. Actually, for my topic, this much explanation and all is not at all required. But then, let me touch it. It is, I cannot go without telling this. So now you must be curious to know more about this small e. I hope maybe you will read about this small e when you come for the next class. This is a wonderful stuff. Okay, this small e. Okay. So now somebody can answer I to the power I. Somebody can answer now. Having explained this, now I think I have given all the inputs to say what is I raised to I. Same.
No, sir, I don't have any idea.
Josmon, are anybody?
Sir, in chat box, Akhil has given some answer.
Wait. Then chat box. പറയാൻ പറ എന്താണ് in the chat box. Akhil has given. Is it 0.207? Yeah. Akhil, how did you get it? You tell. Yeah, you are right. You are right, Akhil. Excellent. How did you get, Akhil? It's a real number. How did you get?
സാർ അന്ന് സാർ ക്ലാസ്സിൽ വന്നിരുന്നത് പോലെ ഐയുടെ ക്ലാസ് എടുത്ത്
അപ്പൊ ഞാൻ ഇത് പറഞ്ഞ
പറഞ്ഞതായിട്ട് ഒരു ഓർമ്മയുണ്ട്.
Oh, okay, okay. At a point 2 exactly as an തോന്നുന്നു. Okay. See, I is here. In terms of exponential, how we can write here? E raised to I pi by 2. This particular point is nothing but, see, if this is e raised to I theta, this is e raised to I into 0, e raised to 0, that is 1. And this is e raised to I pi by 2 raised to I. So you get e raised to I square pi by 2. I square is minus 1. So e raised to minus pi by 2. So it will be a quantity, a small 1 by e raised to pi by 2. It will be 1 less than 1. So what he has told should be the correct answer. It's a real number. You get this particular point, please? Hello?
So can you please explain it once more?
This particular point I is also, what is that? This particular point I is equal to e raised to I pi by 2, correct? This particular point e raised to I theta. So whatever is the angle, e raised to I into that theta, that angle, that is e raised to I theta.
Yes, sir.
This particular point is e raised to I pi, this point. This point is e raised to I pi by 2, and that point is I itself. Correct? You
Yes.
got it? Yeah.
Yes.
So now you raise it to the power I. So you get, what is this? I into I square, you will get e raised to I square pi by 2. That is equal to e raised to minus pi by 2. And this is 1 by e raised to pi by 2. And that's a real number. You got it? Hello, Singh.
So why only at e raised to I pi by 2?
No. At this point, it is e raised to I pi by 2. At
So
this,
we can have a different point also, right?
but here I raised to I have asked. So this I am writing in this way. If it is something else, say minus 1, that I can write e raised to I pi.
Yes, sir.
And there are other things
I got
also,
it.
not only this. You got it?
Yes, sir. Yes, sir.
Yeah, that's right. Okay. Shall we move?
Yes, sir.
Okay. Now you remember, you should know this person. This is an Irish mathematician, William Rowan Hamilton. He lived 1805 to 1865 for 60 years. And he has invented a mathematical stuff called quaternion, which is an extension. In some sense, it is an extension. It's not exactly extension, but similar to that. More or less, it has, you can say, motivated the invention of this by the complex number. And the algebraic relations that he uses is also similar. And he is a great man. And in 1843, when he was walking in October 1843, William Rowan Hamilton, in a flash of genius, discovered the fundamental formula for quaternion multiplication. For the quaternion multiplication, this is I square is equal to j square equal to k square equal to ijk equal to minus 1. It's inscripted, even today it is there in Ireland. Such a great, his discovery is not only a quaternion, There are so many things. Hamilton's principle, Hamiltonian mechanics, then Hamilton-Jacobi equation, quaternions is one of them, biquaternions very interesting, and so on. There are so many things, okay? This is only to introduce that great man as an occasion to tell about him, talk about him. And even he has coined the word tensor, scalar, and all is coined by him. Now, this quaternion, let us first define why you ask rotation quaternion. That's why you want. So let's define and then say what is why I am calling for rotation. See, quaternion means that quarter 4. There are 4 elements. 1, 2, 3, 4 elements called in this way. Together is Q. And the first one is called a scalar part, and the next 3 together is called a vector part. Scalar part and a vector part. Of course, this vector part has got unit vectors I, j, k along the 3 orthogonal axes in the usual way what we study. And this why rotation directly we are going. The quaternion having the 4 tuples, 4 elements, 4 tuples, it can be generalized to 4-dimensional space, a space-time, for example. So it has applications there and many other places with 4 dimensions. But we, in our coordinate transformation, we are interested in rotation. And there it is one of these supermost stuff to use its beauty for computation of rotations, coordinate transformations. So I am calling rotation. When we adopt it, how do we are adapting? That I will tell you. And that is why we are calling rotation quaternion here. Now, you will just say you have an I, you have a J, you have a K here. And they are the unit vectors of orthonormal basis. R3 means the 3-dimensional space. Orthonormal vectors, we know they are of unit length. Each one of them is orthogonal to each other. That is what orthonormal. Also, the I square, J square, K square, that is equal to I, J, K is equal to -1. We will attach meaning to all this. First, take this algebra relation developed by Hamilton. Then I, J equal to, this is nothing but the cross product. I cross J will be K in our conventional cross product. And this is also cross product, you can check. J cross K will be I, and this also will satisfy, you can check this. And K cross I will be J and similar. Now, when I say I, in the 4-element stuff, it takes the second position. Okay? Usually when you say I, we tend to leave all other elements, leave and tell only about I. But really speaking, when I say I, it is actually 0, 1, 0, 0. This is how we have to say, really speaking. I is a quaternion. I is not a single element now. I is a quaternion where this is 0, this is 0, this is 0, this is 1. And that's what is written here. Similarly, J is another quaternion, 0, 0, 1, 0. And K is another quaternion, 0, 0, 1. And each is a quaternion with the physical meaning that we will come. It is not simply telling like this, it has got physical meaning. Okay. Now, what is that physical meaning? Some diagram I am having, I will explain to you. I think before telling this, I think straight away go to that diagram. You see, there is an X, Y, Z frame. I make a positive rotation about X-axis by 180 degrees, and that is signified by I. Our usual complex number I, it was a rotation of a vector by 90 degrees. Here, there is also a rotation of 180 degrees about an axis. There also we had an axis. About an axis, the entire coordinate frame by 180 degrees. By doing this, the resultant will be like this. Okay? You agree? All of you agree? Y will go down, Z will go on the other side. That's what is happening. This is after the rotation. And once more I rotate about the same axis. So I into I square. And that means this comes up, this fellow will go up, this fellow will come as it is. So we restore where we started. X, Y, Z will come back. X, Y, Z after the second 180 degree rotation. Okay. So I square, when you say minus 1, it means 360 degree rotation about the axis X. That means I is 180 degree rotation about the axis X axis. And J is 180 degree rotation about Y axis. And K is 180 degree rotation about Z axis. And I square, when you say minus 1, and this means nothing but 2 times 180 degree rotation gives me minus 1. And if I have to write this, I square is another quaternion. So if I say I square is a quaternion, I should write it as minus 1. See, the position has now changed to the scalar position, the scalar part position, first position. This minus 1 goes to the first position, the rest all becomes 0. And this has got additional meaning. Everything together we did not jumble in this slide. We go forward and note that ijk satisfies the vector cross product. In addition to, please note this point, ijk, they are unit vectors. They satisfy the vector cross product in our usual sense. And additionally, it has the physical meaning. While they have this meaning, along with that, additionally, it also has the meaning of this rotation about x-axis, rotation y-axis, rotation about z-axis. Please remember, when I write this statement is not fully right. I must say, I signifies a unit vector along orthonormal x-axis, and it satisfies ijk cross product. And also it means 180 degree rotation about the x-axis. If I tell all of them together, then only really this meaning of I is told. Here, of course, we are putting parts and parts here and there for the easiness of explanation. I hope I have not explained the physical meaning of this one. ijk we have. So if I is rotation about the x-axis, that is the second position, is x-axis, the position of the y-axis, position of the z-axis. That is why j becomes 180 degree rotation of the y-axis, it comes in the second position. K becomes 180 degree rotation about the z-axis, that comes in the fourth position. Now, so we also found that after 2 I rotations, we restore to the same original point, and that is represented by this quaternion, and that we will further discuss. Now let us take another case, ijk. I is a rotation about x-axis, that gives this particular orientation. Then I give a rotation about my y-axis, the resultant y-axis by 180 degree. That will take to this orientation. And now, suppose this figure and this figure is the same. Suppose I had given one single rotation about z-axis 180 degrees, that would have also given the same thing. Suppose this leftmost figure and the rightmost figure here are one and the same. And if I give one rotation about the z-axis by 180 degrees, I would have got this, which I got through two rotations, I cross, I mean, say not I cross, okay, ij. So these two consecutive rotations is identical to a rotation about this axis, which results in the same thing. So the physical meanings are getting explained when you say this ijk is not simply in the usual way we study. And let's see one more, maybe minus ji. So minus ji, the direction has been changed. Normally the positive direction is like this. So I have changed the direction minus j. And then I, minus ji. I got this. The resultant is this one. That also you see resulting as same as this particular one. So minus ji gives this gives this one. Ij gives this. K rotation also gives this. So Ij equal to K equal to minus Ji. This was one of the Ij equal to K is equal to minus Ji. So this is one of the relation. And this we have already seen. I square, J square, K square are similar. So we have explained one particular, at least a portion of the algebra we have explained. What does it mean? All other things also can be similarly explained. Okay. Now, having done that, so the Q1, Q2, Q3 define that is a vector part, and that now we are going to give another name. These three define an axis of rotation. These three define an axis of rotation. And then this Q0, the scalar part, that defines the amount of angle to be rotated about this axis for the entire coordinates. Okay. Now Q0 is the angle of rotation about the axis defined by this vector, and which I am calling the axis of rotation. And again, we will go on discussing like this because that is the only way to understand quaternion better. Since Q1, Q2, Q3, this vector defines an axis of rotation. See, when I say an axis of rotation, the length of the axis doesn't really matter. So with the direction that is important. I hope you all will appreciate me. The axis of rotation is only a direction. The length doesn't matter. And therefore, if I have the vector, this Q1, Q2, Q3, together I call Q bar, the vector part, the magnitude of this does not really matter to us. Because if I multiply with this a common scalar, the magnitude can increase or decrease, but it doesn't change the direction. So it does not matter if we do not change the direction of this vector. If we change the direction of the vector, then axis of rotation meaning changes. So that we cannot do. What is that it means is, if we multiply this vector part by a common arbitrary positive scalar, then all of them, say suppose lambda q1, lambda q2, lambda q3, will amplify this vector by lambda times. But amplify or contract, but the direction will remain the same. Okay, so the vector direction will not change. And therefore, because I'm going to interpret and use it in this fashion as an axis of rotation, where my vector length doesn't matter, so therefore I choose my vector part as a unit vector, U, having components ux, uy, uz, whose total magnitude is unity. That's what is written here. Then the quaternion becomes Q0 ux, uy, uz. Now this is scalar part. But then the magnitude of the four things together now will be more than 1 if Q0 is greater than 0. But that in our rotation quaternion, that is not allowed. This we have made unity magnitude. This is a non-zero number, means the total magnitude will become more than 1. And that is not allowed. And we want to ensure the magnitude of the whole thing want to be 1, because when we want to use this quaternion for rotation application, rotating a vector or rotating a frame should not change the vector's magnitude, which we are transforming in one frame to another. When we are transforming, I should not alter the magnitude of the vector. And that imposes the condition when quaternion is used for handling rotation, and the magnitude of this Q, when I say Q, the entire Q0, Q1, Q2, Q3, all the four elements together, the magnitude should be 1. Okay. Now, let us slowly graduate. Somebody should tell me the time, because I'm 39. Okay. Q0, now this is the element. Suppose this is a one hypothesis proposal. Shall we take it like this? This is a proposal. Okay. Yeah, we will come to some conclusion. The Q0, let it, already we have told this represent the angle, the amount of angle to be rotated about an axis given by these three elements. Fine, let that angle be called alpha. And then suppose I call this element as cos alpha and multiply these three elements by a common factor sin alpha. Remember, ux, uy, uz is a unit vector, and that all the elements are multiplied by a common factor does not change the direction of this vector, because they are common element. Sin alpha is common to all three elements. Now, so this still the axis of rotation, whichever direction it was originally meaning, ux, uy, uz, that remains the same even after multiplying with sin alpha in all three terms, because they are multiplied with all the three. So the axis of rotation is not changed by this multiplication. Then I have taken cos alpha here. Now you take the magnitude, square this, square this, square this, square this, and add all of them and take square root. You will find, you will get the magnitude is equal to 1. So this form, what is shown here, seems to be all right for my representation of quaternion, because the norm condition it is satisfying without affecting the axis of rotation. Direction is not changing. It should not be changed. Yes, it is not changed. With that, I am able to reach a method to say that my quaternion magnitude is still 1. Yeah, one requirement is met. So the above form said that way is suitable for rotation. But what happens further is that here we'll just more detail we'll talk later. See, we are dealing with only a 3D vector, and we want to transform a 3D vector from 3 dimension to 3 dimension only. But whereas we have a quaternion which has got 4 elements, say, so in some sense this is a 4-dimensional entity. So if you multiply a 3D vector by a 4-dimensional entity, then we will unwantedly get a 4th component. And how do we interpret it? How do we get rid of it if you want to use this for representing coordinate, handle coordinate transformation? So in that sense, we have some additional restriction. That's what is written here. since we are interested in transforming a 3D vector to 3D, and since quaternion has effectively 4D, the transformation from 3D to 3D requires a certain modification of this. This form is okay, but it requires a slight modification, which we will discuss just afterwards. Now, before that, we just see, suppose two quaternions are given. A P is a quaternion, P0, P1, P2, P3, and Q is a quaternion, Q0, Q1, Q2, Q3, and the product is simply algebraically expand. I have simply taken P0 into this term, P0 into the second term, P0 into the third term, fourth term, then this term into the first term, this term into the second term. That's what is written, nothing more. And then use the quaternion algebra rules. I square is -1, ij is equal to k, ik you find out from the table, or you can, from your mind, you can work out. You put all that simplifications, and you can concisely write a 4 by 4 matrix into a 4 by 1 quaternion. So as a matrix product you can write. Okay, this you can check. Now, here we said this form appears to be okay. Now I am going to propose to you, suppose I modify my proposal of representation. Still alpha is the angle of rotation is fine, but then my Q0 I will take, instead of cos alpha, if I say cos alpha by 2, I call it Q0. And other ones, 3 components are multiplied by sine alpha by 2. Here also, this vector, the direction is not changed. That is the axis of rotation. This 3 says the axis of rotation, that is not changed because still the common factor is the same. And cos alpha by 2, still the total magnitude is still unity. So this is also okay for me. And let's check that 3D to 3D vector transformation, whether this is okay or the previous one is okay. Previous one means this. The new proposal is this. Which one is? Now, now before going further, I want to tell you. See, the ux, uy, uz, this unit vector. This is actually the eigenvector of our DCM matrix between the frames F1 to F2, for which this quaternion is defined. See, in the very second class, I think, I was talking about this eigenvector in our coordinate transformation. See, it is again coming. And this is nothing but the eigenvector of the DCM matrix between these two frames. And that is this one. And of course, that unit vector is scaled by something else, that you don't worry, the direction is not changed. So observe this particular point is very, very important. So you need to look at here, when we transform a 3D vector, let's say V, capital V in frame 2 to frame 1, having a quaternion Q from frame 1 to 2, remember these statements have to be replicated exactly the same. V is from V, we want to transform from frame 2 to 1, and Q is the quaternion from frame 1 to 2. The problem of fourth dimension can be got rid of if we do the following operation. Now suppose V is a vector in frame 2, and this I want to represent in frame 1. And using quaternion, how it can be achieved is, we take this Q, and this is the quaternion multiplication, and this the vector is written as a quaternion. One 0 element is added to make it a 4 element staff, and then quaternion multiplication with the conjugate or inverse of the quaternion, same quaternion. If you do this operation, you get this W vector That is the same vector V now gets represented in the frame 1. Now, this, you see the Q star, 2 times it is coming. Our angle of rotation about the axis, eigenaxis, is alpha. Because 2 times the Q is coming for this transformation, this alpha by 2 is the right choice. Because 2 times it applies, alpha by 2 into 2 will be alpha. Our requirement will be totally met. Okay. The above form, this one, transforms a 3D vector to 3D vector in different frames F1, F2. Effectively, Q appears twice as Q star. The alpha by 2 gets applied twice and the net angle is alpha. So therefore, this is the right choice which satisfies all our requirements required for a rotation quaternion. Okay. Now, suppose you want to write the reverse. The given vector is in F1 and you want to represent the vector in F2. Earlier the Q star was here, you take it here, and the Q was here and take it here. Do the same operation, you will get it. Okay, so that's all about it. Then let's quickly go through some of the properties of the quaternion. Q0 is cos alpha by 2. And Q0 square, you square all of them, it will be 1 because norm is 1. You take the square root is also 1. The last 3 elements you square and take square root, you will get sine alpha by 2, that common factor getting multiplied to each component. And U is nothing but this. And Q inverse is simply cos alpha by 2 minus the vector part is negated. The scalar part remains the same. That is, Q0 is kept as it is. This entire vector part is sign is changed. Then you get Q inverse. And this is also called conjugate. And conjugate and inverse are the same. And Q inverse is equal to 1. 1 means 1, 0, 0, 0. It's a 1 as a quaternion you have to look at. And quaternion multiplication is non-commutative. You cannot change Q1, Q2 is not equal to Q2, Q1. It's not commutative. The unit vector we already told. The unit vector of the vector part is the eigenvector of the DCM corresponding to the eigenvalue plus 1 of the DCM. 9. The conjugate and inverse are the same. And we can get the DCM matrix from this quaternion easily. So these are the summarizing properties. So now, having said all that, now I will say I have 2 frames, an I frame, xi, yi, zi, xb, yb, zb. This is also orthogonal. The drawing may be looking shabby, but it's orthogonal. This is also orthogonal. Their angular orientations are different. Now, connecting these two, there is a transformation matrix or DCM, and that has got a eigenvector corresponding to eigenvalue plus 1, and that eigenvector is this vector u, which is a unit vector in the vector part of our quaternion. And about that vector as an axis of rotation, you rotate this frame, the entire frame about this axis, give a rotation alpha, you will align this frame to this exactly. And that's all. So each part of the quaternion is explained by this statement. So in order to tell this, only I was building my background. So otherwise, these are all, this we have already explained. Okay, let me repeat. We have 2 frames, I frame and B frame. Their angular orientations are different. They are orthogonal. Each one of them are orthogonal. relating them, there is a transformation matrix or DCM. That DCM matrix has got an eigenvector corresponding to its eigenvalue plus 1. That eigenvector, I take it to reduce its magnitude, maybe unity or lower. The direction remains the same. That is that eigenvector. And use this eigenvector as axis of rotation about which the first frame is rotated by an angle alpha, and then this frame will align exactly with this frame. This is what the quaternion says. Okay. If somebody wants to repeat, I'll repeat. Okay. Yeah. Now, how to derive this? For that, you have to do what you have to do. You have to do this explicit quaternion multiplication you have to do and then get those terms. So this, it looks a lot of terms are there, but then it's very easily definable. So this is a DCM matrix from F2 to F1. And if you want the DCM of F1 to F2, simply take the transpose of this. Now let's take a little bit, a small example. What is the time now? 54. Okay. Let's take an example, X, Y, Z axis. And I give a rotation about this Z axis by alpha and get my X to X dash and Y to Y dash alpha, and then take a unit vector along X dash. My F2, I call the new X dash, Y dash, Z is my F2. My F1 is X, Y, Z here. I am taking a unit vector on X dash and calling it as I, a unit vector on this axis. And that I'm calling a vector, this is a vector, therefore that vector is simply I, 0, 0. And this I want to transform to my old frame. This is in the rotated frame. Rotated frame is X dash, Y dash shed. This I is on that frame, represented in this way. Now I want to represent this in the old frame X, Y, Z. That's what I'm trying to do. It's a very elementary example to see how it works. What is my eigenvector? I have two frames now, X dash, Y dash, Z, X, Y, Z. There is one is F1, F2. Between them, there is a transformation matrix. We know it already. We have written, studied earlier. And what is its eigenvector? The eigenvector is simply in this case Z. Z itself is the eigenvector. And that's why the third position, U, the vector part is simply 0, 0, K. So Q is cos alpha by 2 plus U bar sin alpha by 2. Of course, U bar becomes first two elements 0, therefore I explicitly write the Q is cos alpha by 2 plus K sin alpha by 2. And Q conjugate is, this sign is changed here. Now we need to transform this I vector in F2, X dash, Y dash shed is my F2, that the vector I is there, to F1. So now I have Q star, and then my I. All the three are there, required to do this transformation. So this is Q into I into Q star. You simply, this is simply an expansion, algebraic expansion. Only thing where it comes Ki, you have to substitute from what is the cross product of Ki is J, and Kj is minus I. You substitute those things. Then you come I into something, J into something. There is nothing but I cos theta J, sorry, I cos alpha, j sin alpha. And exactly, you look at here, this unit vector, if I represent is the x component, is this I into cosine of this alpha. And the y, this is 90 minus alpha, and therefore, of course, this axis has got j unit vector, therefore, j sin alpha. So that is exactly I am getting I cos alpha, j sin alpha. Then you may ask, sir, this is a very simple problem. You want to represent in this frame and then want to take in this frame simply, you can take, could have taken like this. Yes, you could have done that. But that simple example, I am utilizing to demonstrate the formula which is used to transform using quaternion to make it this one. So the vector in F2 is I, the same vector in F1 is I cos alpha, j sin alpha. Okay. And now you see, we have taken alpha, cos alpha by 2, sin alpha by 2. And we have done this operation, Q, I, Q star. See, finally we got alpha, alpha. See, alpha by 2 we have taken. As we anticipated, because Q comes 2 times as Q and Q star, twice this alpha by 2 will come, therefore net angle will be alpha, and it really happens. It really happens. That's what is demonstrated here. And if somebody is interested, this new vector is it in now F1. You take that F1 here, and if you want to transform to F2 backwards, then you have to do Q star, that vector, this vector, into Q. So I have done that, and I must get my original I vector. And I really got that vector. You can also do that, even though it looks it is simply algebraic manipulation only. I got it. So this is correct. It is verified. So I think I will tell this and then stop today. So we accepted the quaternion having 4 elements, and these 3 elements represent an axis of rotation, and also this represents the eigenvector of the BCM matrix connecting the 2 frames under question, and this is a function of the angle to be rotated about this axis. I repeat that statement. Actual angle to be rotated is alpha, but this element is a function of alpha. Alpha is the angle. The function of the alpha is cos alpha by 2. It doesn't matter. Still, it is trying to tell that angle in some way. That's all. So this talks about, this gives the angle information to be rotated as a function of angle, and this is the axis about which that rotation needs to be done. So this we have accepted. The quaternion is now well defined. Its norm is unity. Then I is easy, as we have already told this. So I square is 2 quaternion multiplication, and I square is -1. We know the position should change. So when this position is changing, what does it mean? This position is cos alpha by 2. It means cos alpha by 2 is equal to -1. That means alpha by 2 is pi. That is, alpha is 2 pi. That means you have rotated 360 degrees. That's what it means. Then, if that is so, I can, -1 can be made 1 also. It doesn't matter. They are equal. -1,000 is equal to 1,000. That way. Okay? Now, I hope you understood this. The earlier we told, something more is told now. Now in general, one observation, there is a possibility that this Q0 may sometimes go negative. When Q0 goes negative, less than 0, then it means alpha is greater than 180. then you simply negate all the elements. If this becomes negative, you negate all the elements, they still be equivalent. They still be equivalent. For that, we will take a simple example. Let's take this Q0 is minus 1 by root 2. It means alpha by 2 is 135 degrees. That is, alpha is 270 degrees. Pictorially, and this vector is nothing but Q1, Q2, Q3 vector is shown like this, and a rotation of 270 degrees about that. Now, when I negate all these things, what will happen? Q0 earlier was minus 1 by root 2. That will become now minus Q0 will be 1 by root 2. 1 by root 2 is means alpha by 2 is 45 degrees, alpha is 90 degrees, and this vector is now changed sign. So the vector upward earlier it becomes downward. Wherever it is, it will be the opposite direction. And then the positive rotation about that alpha is 90 degrees. And this are equivalent. Same angular position it will go to. And therefore, then Q0 becomes negative. And if you change the sign of all of them, they are equivalent when Q0 is less than 0. So I think derivative of this thing we will go to the next session. So with that, I think today's thing I will stop and we will start some few questions. Yes. Yes. Ratnendra Singh,
Yes, sir.
you have studied quaternion there. How do you feel now?
We haven't studied quaternion. We were just introduced by it so that it is used for rotation. So now it's good, sir. Now I can understand something. I can relate to that.
Okay. So, is there any doubt in our discussion today?
Yes, sir. But doubt is there, but I think I have to study it again once again. Then I can get it cleared.
Okay, doubt is there. That's a good sign.
Yes.
Okay, Josmon. Josmon.
Hello, sir.
Josmon, ഇത് ഇൻട്രസ്റ്റിംഗ് ആയിട്ട് തോന്നിയോ ഈ ലെക്ചർ? അറ്റ്ലീസ്റ്റ് ആദ്യത്തെ കോംപ്ലക്സ് പ്ലെയിനിലെ ഞാൻ യൂണിറ്റ് സർക്കിൾ ഒക്കെ വരച്ചു, അതൊക്കെ ഇൻട്രസ്റ്റ് ആയിരുന്നോ?
അത് കുറച്ചൊക്കെ ടച്ച് ഉള്ള കുഴപ്പമില്ലായിരുന്നു.
Okay, we will, don't worry. Next one session we will dedicate for you people to clarify the previous lecture, so that I want you to take you people also along with, so that it will become useful. Anything you want to ask? Nobody? At least this figure, somebody wants to ask anything? It's a very interesting thing. This is not quaternion. This is a very all, I think this small e is a hero. It's very interesting. And you see, this same thing, the projection of this vector as it is rotating like this, if you take the projection on the x-axis, you get the cos omega t, you get. And that is nothing but your simple harmonic motion in mechanical engineering. Of course, two sinusoids at 90 degrees giving rise to the circle. So in civil, mechanical, everywhere they study simple harmonic motion is nothing but the sinusoidal motion only. In signals, in Fourier transform signals, you have cosines and sines. That is nothing but the same thing only. Of course, we are coming out of the quaternion. And here there is an eyeless identity. There are many, many lectures available in the YouTube and other internet media. It gives more insight into this. Is phenomenally, I mean, what do you call it will occupy your mind forever. Such explanations are there. Please go through that. And this small e, if during any of our lecture, if an opportunity like this comes, we will talk about it a little bit. Otherwise, if somebody wants to talk, I can dedicate a session for this. Okay. So I think if you have no other question, I think then we should stop here. So Jinju, you can take over.
Okay, sir. Okay, sir. Vibin? Is Vibin is here?
Yes, miss.
Okay.
Good evening, all. On behalf of VC Department, I, Vibinam K of S4EC, take this opportunity to propose vote of thanks. First of all, I extend my most sincere thanks to the Almighty God for making today's session a grand success. I would like to express my gratitude to our principal, Dr. P.P. Mohanlal, for his excellent presentation and making the session interesting and meaningful. Thank you, sir. Last but not the least, I would like to thank all the participants in this webinar. Once again, thank you all.
Okay, thank you very much.
Thank you, sir.
Shall I stop the recording?
Yes, sir. Yes, sir.